AcePhysics.org, Math and Physics Tutoring with Dr. Hudis. Unraveling the train and tunnel paradox. Visuals, explanations, and Lorentz transformation. In this presentation, I'm going to discuss one of the quintessential problems in relativity, the train and the tunnel, or the barn and the pole paradox, where observers from different reference frames measure different lengths of an object moving at relative speeds to them. So next I will discuss the paradox, and I'm going to go through some calculations as well. Imagine there's a train, and the train is driven by Larry. There's a tunnel. There's a tunnel. You can see that's the tunnel right there. And the tunnel is half the length of the train when they're both at rest. If they're both at rest, the train is twice as long as the tunnel. In this picture, Larry's not moving, Chris is not moving, Bo is not moving, the tunnel's not moving, the train is not moving. Everybody's at rest. And I've assigned length values. So the train is 6 times 10 to the 8th meters long, and the tunnel is half the length of the train in their rest frame, and that's 3 times 10 to the 8th meters long. These are numbers that I'm going to use for this problem. Obviously, that's an incredibly long train and an incredibly long tunnel, but it's going to make the calculations easy and allow you to understand the ideas of relativity better. So let's imagine that Larry is moving at 0.866 times the speed of light, and Larry's moving to the right. What do Chris and Bo see? Well, Chris and Bo see Larry move to the right, and Larry's length is contracted. The reason his length is contracted is because relativity says when objects move, their length contracts in the direction of motion, and so Larry's train is contracted. It's contracted to half of its original length, half of its rest length, because the speed that I chose, 0.866 c, and Chris and Bo see that Larry's train fits within the tunnel, and it drives by, and that's just what Chris and Bo see. You can ask the question, what is it that Larry sees? Well, Larry says that he's at rest. Larry and the train see the tunnel, Chris and Bo, and everything attached to their reference frame moving past Larry at negative 0.86 times the speed of light. From Larry's inertial reference frame, he sees that the tunnel shrinks to half of its rest length. Now only 1/4 of the tunnel fits Only 1/4 of the train fits within the tunnel, and the tunnel and Chris and Bo move past Larry, and they have shrunk. What does Einstein's special theory of relativity tell us? The formulas on the left are the formulas for length contraction and time dilation. I'm just putting those out there. I'm not deriving them. From the reference frame of Chris and Bo, they are at rest, and Larry is moving with a relative speed of 0.866 c. Chris and Bo see that the tunnel is 3 times 10 to the 8th meters long, and the train is length contracted to 3 times 10 to the 8th meters long. This picture is the picture that Chris and Bo see. From the reference point of Larry, the train is at rest. He is at rest, and the tunnel, Chris and Bo, are moving with a relative speed of v equals negative 0.866 c. Larry sees that his train is 6 times 10 to the 8th meters, and the tunnel is 1.5 times 10 to the 8th meters. The tunnel has been length contracted. Einstein's train and platform thought experiment. Chris and Bo measure the train to be 3 times 10 to the 8th meters long, and the tunnel to be 3 times 10 to the 8th meters long. Larry measures the train to be 6 times 10 to the 8th meters long, and the tunnel to be 1.5 times 10 to the 8th meters long. How can they measure different values? What is Einstein's solution to this problem? Bo and Chris measure the train by marking the track simultaneously at the front and back of the train. How will Larry perceive this measurement? By analyzing this, we'll come up with the solution to the problem. In order to measure the train is moving past them, and right when the train gets in the tunnel, Chris and Bo simultaneously mark the track at the front and back of the train, make marks on the track. And then Larry drives off in the train, and these marks are left there, and then Chris and Bo can measure the distance between the marks, and then they find the length of the train, and they also would find the length of the tunnel because the marks are at the front and the back of the tunnel by design. That's what this problem is set up to do. That's how Einstein set this up. It doesn't have to be that way. It just makes it a little more fun to have a tunnel involved. All right, to analyze this, we need to discuss moving and stationary coordinate systems. Moving systems are referred to as prime systems and are in motion relative to another coordinate systems. And the Lorentz transformations are the equations that we're going to use, which will allow us to determine the space-time coordinate of an event in one system based on our knowledge of the event in another system. In the rest frame of the tunnel, which is Chris and Bull's reference frame, they're in the rest frame, so there's going to be an x-axis. The stationary reference frame is the x-axis, and it measures events relative to the origin of the stationary inertial reference frame. That's what I've drawn here. And we choose to put the origin at the front of the tunnel. The origin you can put anywhere, but we're going to put the origin at the front of the tunnel for the stationary system. And this is how Chris and Bull measure events based on this coordinate system. Now, Chris and Bull will see Larry moving by on his train, and he has an x prime system, which means there's going to be a coordinate system attached to the train. The coordinate system isn't real. It doesn't have mass. It's just there's going to be some coordinates relative to the front of the train. The moving reference frame, the x prime axis, measures events relative to the origin of the moving inertial reference frame. And notice, as Larry moves, the reference frame moves with him. The origin always stays at the front of the train. The x prime axis moves with the train. Now, from the reference frame of Larry, Larry is not moving, and the tunnel is moving to the left. So in this case, the stationary coordinate system is the x-axis, and that's going to be at the front of the train, and that doesn't move. There's also a moving coordinate system. And in this case, the moving coordinate system is attached to the tunnel. And just like before, the origin of the moving coordinate system is at the front of the tunnel, which is right here. But now, as the tunnel moves past Larry, the origin of the coordinate system moves because it stays at the front of the tunnel. The Lorentz transformations allow us to determine the space-time coordinates of an event in one system based on our knowledge of an event in another system. These are the Lorentz transformations. It's t prime equals gamma times t minus vx over c squared. And the space transformation is x prime equals gamma times x minus vt. Gamma is the Lorentz factor. It's 1 divided by the square root of 1 minus v squared over c squared. The Lorentz transformation equations, coupled with the distance formula, form the mathematical foundation for comprehending Einstein's special theory of relativity. You see Larry is driving his train at 0.66 times the speed of light. He's passing Chris and Bull, and he's halfway out of the tunnel, and an event happens. What is an event? Event could be anything that gives off light, which is almost anything, but we'll call it a firecracker exploding just for simplicity. Anything can be an event. It could be a person tripping. It can be anything happens. There's an event that happens at this space-time position. Now, that event happens at some position x prime away from the front of the moving coordinate system, which is attached to the front of the train, and it also happens at some x location relative to the front of the tunnel. So x prime is the distance away from the front of the train, and x is the distance away from the front of the tunnel. And so if an event happens at x prime and t prime in Larry's inertial reference frame, it happens at x and t in Chris and Bull's inertial reference frame. And it's not just the x that transforms, it's also the t that transforms, which is different than in Galilean relativity. Now let's analyze the barn and pole or train and tunnel paradox in special relativity. In the rest frame of the tunnel, event 1 is the front of the train passes the front of the tunnel. Well, the front of the train is defined to be x prime equals 0. And the front of the tunnel is defined to be x equals to 0. And at this time, we're going to say that both Larry and Chris start stopwatches. So Chris and Bull have a stopwatch, which is the red t equals 0 at the bottom. And Larry has a stopwatch, which is the yellowish stopwatch on his train. And right when the front of his train passes the front of the tunnel, they both start their stopwatches. This event happens at x equals x prime equals t prime equals 0. That's event 1. Front of the train passes the front of the tunnel. Now what about event 2? Event 2 is the front of the car or the train reaches the back of the tunnel. And I'm going to show you how I get these numbers. So that happens at a time of 1.15 seconds in Chris and Bull's stationary reference frame, and it happens at a time of 574 seconds in Larry's reference frame. And we're going to go and work out these numbers using the Lorentz transformations. So first of all, equations 1 and 2 are the Lorentz transformations. What is the information that we know? We know that x prime is equal to 0. Why is x prime equal to 0? Because it's the event where the front of the car, the front of the train, something happens at the front of the train. Well, the front of the train is defined to be x prime equals 0. We also know gamma equals 2 because the speed is given, and if you're given the speed, you can work out gamma, and I chose that the speed is 0.866 c, so gamma is equal to 2, which is an easy number to work with. Why is x 3 times 10 to the 8th meters? Because in Chris and Bull's reference frame, they measure their tunnel to be 3 times 10 to the 8th meter. And that's the rest length of the tunnel, and the event is that the front of the car reaches the back of the tunnel. Well, the back of the tunnel is a distance of 3 times 10 to the 8th meters from the front of the tunnel in the reference frame of Chris and Bull. And so we also know x and we know v. And so therefore, we can use equation 1 in order to solve for t. So equation 1, x prime equals 0, gamma is 2, x is 3 times 10 to the 8th, we know v, and we can solve for t, and this tells us that t is 1.153 seconds. Now we know x prime, gamma, x, v, and t, and so with this information we can solve for t prime, because t prime equals gamma times t minus vx over c squared, and we know t, and we know all of this information, therefore we can get t prime. So event 2 is the front of the car reaches the back of the tunnel. In the unprimed coordinate system, this happens at an xt space-time coordinate of 3 times 10 to the 8th meters and 1.15 seconds, and this happens at an x prime t prime space-time coordinate in the moving reference frame of 0 and 0.574 seconds. Okay, now let's discuss event 3. Event 3 is the back of the train hits the front of the tunnel. So when the back of the train hits the front of the tunnel, that's the event corresponding to this black arrow right here. And that happens at a time of 1.15 seconds in Chris and Bull's reference frame and a time of 2.3 seconds in Larry's reference frame. I'm going to show you how I get these numbers on the next slide. So event 3 is the back of the train hits the front of the tunnel. Well, we know gamma is 2 and we know x is equal to 0. Why is x equal to 0? Because the front of the tunnel is at the location of event 3 and the front of the tunnel is defined to be x equal to 0. We know the velocity and we know t equals 1.153 seconds because this event is simultaneous to the, and so this time is the same time as event 2. So we know t as well. Now what we can do is we can solve for x prime, which is going to be the location of event 3 in Larry's coordinate system, and we can use equation 1, x prime equals gamma, x is equal to 0, v is negative 0.866 c, and we know t, and therefore x prime is equal to negative 6 times 10 to the 8th meters. And so in Larry's coordinate system, he sees that the event happens 6 times 10 to the 8th meters behind the front of the train. For event 3, we can also solve for t prime in Larry's coordinate system. We know gamma, we know x, we know v, we know t, and we know x prime. T prime equals gamma times t minus vx over c squared, and this tells us that t prime equals 2.3 seconds. So the space-time coordinate system of event 3 in Bull and Chris and the tunnel's reference frame is 0 and 1.15 seconds, and the space-time coordinate in Larry's reference frame is negative 6 times 10 to the 8th meters and 2.3 seconds. Now we have all of the information to discuss the complete picture of the train and the tunnel paradox in Einstein's special theory of relativity. Yes! Yes! All right, now I'm going to show you the full picture. We're going to begin by looking at this from the reference frame of Chris and Bull. Chris and Bull see Larry driving to the right at 0.866 c. When the front of Larry's train gets to the front of the tunnel, Larry starts a stopwatch and Chris and Bull start a stopwatch in their inertial reference frame. Both times say 0. Then Larry keeps driving and he drives into the train, and right when he he drives into the tunnel. He's in the train already. Right when he gets into the tunnel, Chris and Bull simultaneously mark the track. And they do this when their stopwatch reads 1.15 seconds, because that's how long it takes for Larry to drive from the front of the tunnel to the end of the tunnel. And then Larry drives away, and Chris and Bull say the length of the tunnel is 3 times 10 to the 8th meters, and the length of Larry's train was 3 times 10 to the 8th meters. What does Larry see? From Larry's point of view, the tunnel is moving to the left, at a speed of negative 0.866 c. Right when the front of the tunnel reaches the front of the train, both Larry and Chris and Bull set stopwatches in their inertial reference frames. The tunnel moves past the train, and at t equals 0.574 seconds, Bull marks the front of the train and the back, marks the track at the front of the train and at the back of the tunnel. Then the tunnel moves forward, and then Chris marks the front of the tunnel at the back of the train at time t equals 2.3 seconds. And so Larry concludes that Chris and Bull did mark the tracks, not simultaneously though, and Larry says the distance between your marks is 1.5 times 10 to the 8th meters. The distance of my train is 6 times 10 to the 8th meters because the tunnel moved a distance of 4.5 times 10 to the 8th meters in the time between marking the tracks. And we know that the change in time between marking the tracks is 2.3 seconds minus 0.574 seconds. So the change in time is 1.726 seconds. Delta x equals velocity times time. Larry sees that the velocity of the tunnel is negative 0.866 c. The time is 1.726 seconds, and therefore delta x is approximately, with rounding, negative 4.5 times 10 to the 8th meters. And Larry sees that the tunnel is 1.5 times 10 to the 8th meters, and therefore his train is a distance of 6 times 10 to the 8th meters, and it's all consistent. And this is what they see from their individual reference frames. A problem can also be analyzed from the rest frame of Larry, and this is a good exercise to do. You'd start it over from the beginning. In this case here, the velocity is equal to negative 0.866 c, and so the Lorentz transformations you'd flip the sign because the velocity now is negative. When you put a negative velocity in, you get a positive down there. So these would be the two new Lorentz transformations. You'd get all the same answers if you analyze the problem in that way. This has been an episode of Ace Physics Tutoring with Dr. Hudis. Please like and subscribe. Let's learn some physics, ladies and gentlemen.